Hello everyone, myself Priya Singh. Me and my team member are presenting paper on data-oblivious algorithm for multicores, which is presented by Vijaya Ramachandran and Elaine. So these are the topic which we are covering in our presentation, that is history, introduction, the motivation for this paper, then what is data-oblivious algorithm, then binary fork join algorithm, butterfly short algorithm, the results of this paper, and the conclusion of this paper. So let us first see the history. That is, why do we need data-oblivious algorithm for multicores? So in our computer, multiple processes are running. Some processes are run by us, which is user-defined application, and it uses lots of sensitive information like password, username, and everything, etc. While some processes are run by OS to manage computer and also to provide security to such information like password, username, and everything at its level. So the processes which are run by the OS have higher priority and it can access data from any application at any given time. So someday if there is bug present in the OS, so by using bugs in OS, hacker can execute some processes which is not designed by OS but by hacker, and hacker can set the priority of that process high. So now it can access, this process can access data from any application. It can have access to all the information, all the sensitive information like password, username, and everything. So there is a problem. So to solve this problem, Intel brought a special feature known as a software card extension known as SGX, which provides security at the CPU level. So what is this SGX? Let's see. So SGX is basically an instruction set present in CPU, which provide protected area known as enclave for any application. And this enclave is out of reach of operating system also. So let's take an example. If any application now want to access the sensitive data stored in enclave, it must tell the CPU, because the application cannot access the data in the enclave by itself. So it must, it have to tell CPU to execute the enclave by using function present in the CPU itself. And this enclave is saved on the hard disk by encrypting it with the key present in the CPU. So the enclave is encrypted by using key in the CPU and it's stored on the hard disk. And even if you use this hard disk with the enclave with any other processor, this enclave will not be get executed because every processor have their different key. So in this way, even if hacker hack OS bias, he won't not get access to the enclave because it requires processor key. Hence, secure processes such as Intel SGX with hyperthreading become widely adopted. Now let's see the introduction. That is, what is data-oblivious algorithm? So as we have seen in the previous slide, to avoid data leak, Intel have designed SGX, but it also have some issue. Let's see with an example. Okay, suppose, imagine there is a client who outsources an encrypted data to an untrusted cloud server, which is equipped with secure multi-core processor architecture, that is Intel SGX with hyperthreading, and all the data contents are encrypted by using key in the CPU to the secure processor secret key, both at rest and in transit. Then this data is decrypted only by using that key which is present in the processor, as we have seen in the previous slide. So data is decrypted only inside the secure cores, hardware sandboxes where computation takes place. But however, it is well known that encryption alone does not guarantee privacy, right? So it doesn't guarantee that once the data is encrypted, there will be no data leak, your sensitive information will be secure. There will be a data leak, even if your information is in the encrypted form. So to solve this problem, they are trying to design an algorithm whose access pattern distribution do not depend upon the secret input. So such type of algorithm are called as a data-oblivious algorithm. Now let's see the motivation behind this paper. So as we have discussed in the previous two slides, that is, first thing is maintaining the data privacy, which is needed in many applications. Then there was also some previous study before this paper in which they are trying to implement the data-oblivious algorithm by using PRAM model to capture parallelism. But PRAM model does not capture the realistic multicore processor, nor does it reflect parallel programming models adopted in practice. So this paper is trying to remove the PRAM model and is trying to present like this thing in this paper. Then as we all know that I have till previously that there are some prior work going on the data-oblivious algorithm in which they are adopting PRAM model as the model of computation. But the global synchronization between the cores at each parallel step of computation in a PRAM algorithm does not best capture modern asynchronously. Hence, this paper is presenting how multi-core architecture places multiple process core and bundles them as a single physical processor. The objective of this paper is to create a system that can complete more tasks at the same time, thereby getting better overall system performance. We will see this in the further discussion. Then the next motivation is like, as we have seen that even if the data is encrypted, it's not completely secure. So for that, this paper has been like research like to that because the encryption and stored and transmitted data keeps data values private, but access pattern during the computational may leak information. Then the next thing is that the data-oblivious algorithm is an algorithm whose memory access pattern is independent of the input values. Then this paper also is necessary because it provides the algorithm that are cache agnostic, because as cache are the frequently used data, and if that data is leaked by some other application, then it will create problems. So in this paper, they are trying to get a cache efficiency improved. So the further part will be explained by my team members.
Next, we have data-oblivious algorithm. A data-oblivious algorithm is algorithm whose memory access pattern does not depend on its input data, and thus this algorithm captures the privacy and security requirements of a program. The data-oblivious algorithm uses the classical PRAM model to capture the parallelism. PRAM is used for parallel algorithms where multiple processors are connected to a single block of memory. However, it has been observed that the PRAM does not capture the realistic multicore processors, nor does it reflect the parallel programming models adopted in practice. And hence, this paper is presented on data-oblivious algorithm for multicore architecture, where parallelism and synchronization is expressed. This algorithm is also a cache efficient. We will see what is cache efficiency in upcoming slides.
So how binary fork join works? So as she explained, we are for the cache efficiency. So this is a part of the binary fork join. The execution of the binary fork join algorithm starts at a single processor, where every processor has their own cache. The thread can also rely on a fork operations to spawn two tasks, and the fork parallel task can be executed by the other processor as determined by the scheduler. The two tasks will later join, and the corresponding join serves as a synchronization point. Both spawn tasks must complete before the computation can proceed beyond this join. And this gives rise to the series parallel to the computational DAG.
Next is cache efficiency in a binary fork join. So the cache efficiency is calculated on the number of cache hits or missed, and the cache complexity is the total number of cache missed during the execution of a program. The fork join algorithm are designed with the small work, small sequential cache complexity, and small span. The current best binary fork join algorithm for sorting is SPMS, that is sample partition merge sort. This sample partition merge sort has span of big O log n log n with optimal cache complexity. This SPMS, that is a small sample partition merge sort algorithm, is an best algorithm, but why it is not used in this paper is because it is not data oblivious, and no non-trivial data oblivious parallel sort algorithm for optimal cache complexity was known prior to this paper.
Next, this is the part of data oblivious work, as she explained about the cache efficiency, where the data oblivious extend to the computational within the cache. So here is the multi-threaded model that used CREW binary fork join algorithm, where fork and joins are paired. So this is the shared memory machine with processor P, and each with a primitive it which a private cache. Well, this is a well-structured algorithm where they don't use atomic operations or concurrent write in this algorithm. They also designed this algorithm that have a good cache agnostic cache bounds. Next, by using this algorithm, what are the performance metrics they got in this paper? That is like the work of the multi-threaded algorithm, it is executed at a single processor. And thereafter efficiency is a multi-threaded algorithm with binary fork join is measured through the following metrics. First is the algorithm's total work, where that is the sequential execution time. Their cache complexity, the number of cache they misses in the thread, and its span, that is the length of the longest path in the computation deck. Here we have here is a comparison of the CREW fork join model with the prior results, including this CRCW PRAM step simulation work. They have same bound as the sort bound. Using this above results like this, the CRCW PRAM simulation work, data oblivious algorithms for they get the after using this result, they got some other they get the other problems of the data oblivious algorithms, like the tree contractions, connection comparison, MSF. And after comparing this, they improve the span over previous insecure method, because the previous algorithms did not use the simulations route. They also match the previous bounds for other problems like the list ranking and Euler-Tour tree. So after comparing this work, like the prior results, the O n log n, the work, span, and cache, they get the better result by using the binary fork join algorithm.
Next is why binary fork join algorithm is used. Here one can consider multi-way fork instead of the binary fork, but the reason binary fork join is used, since the multi-threaded algorithms with nested binary fork joins have good scheduling results under the randomized work scaling. And the focus of this paper is on CREW multi-threaded model with binary fork joins, where CREW is concurrent read exclusive write, where all the processors are allowed to read from the same memory location at the same time, but are not allowed to write to the same memory location at the same time. And that's the reason this algorithm is used. And this also achieves the synchronizations, and any pair of fork join computations are either disjoint or one is nested within the other in this algorithm. The next we have is binary fork join simulation of PRAMs. The new data oblivious algorithm also gives rise to the oblivious simulation of CRCW PRAMs. The CRCW is concurrent reads and concurrent writes are allowed. And there are two sections of space bounded PRAMs. One is binary fork join simulation of space bounded PRAMs, and another is binary fork join simulation of large space PRAMs. The simulation of small space bounded PRAMs, the first one, is useful or is efficient if the space consumed by the original CRCW PRAM is small. And the PRAM simulation on this binary fork join works as follows into the three steps. One is read step, another is local computation step, and the write step. So the read step is whenever we perform a read request, that time every request obtains a fetched value from memory array, and the write step performs the write to the memory array whenever we perform any write operation. The next second simulation is simulation of large space PRAMs. This is efficient if the space consumed by original CRCW PRAM is large, and this obtained using a butterfly sort. The butterfly sort network is designed to sort the elements with the largest number at the bottom. So there are some other primitives also used in this paper to obtain the oblivious simulation of CRCW PRAMs, just like oblivious sorting. These primitives have been core to the data oblivious algorithms literature and in constructing oblivious parallel RAMs schemes. So the other primitives used are aggregation in a sorted array, propagation in a sorted array, then the scientific method and the oblivious bin placement.
We after comparing all this all the algorithms, and we got the final results for this algorithm where it guarantees that the cache efficiency and the better performance, where the data leakage is the minimal and the cache access timing. It also shows how to get the privacy for free for a range of tasks in a parallel computational model. And the third is it does not incur additional overhead during simulations than the previous work.
Okay, like we have two algorithms which are discussed in the paper. One is binary fork and the other one is butterfly sort. So binary fork has already been discussed before. So now we're going to discuss about butterfly sort. This is also a data oblivious multi-thread algorithm, which is highly cache efficient, and it's also involves the usage of sorting methods. And this algorithm will also be useful for memory access without leaking the actual information, or it doesn't depend upon the input size or the actual input. So if you go to the next slide. So let us now look into how this butterfly sort will work. So this butterfly sorting, which actually involves the usage of special network called butterfly network. So let's take an example of this butterfly network as is called an abstract network. Let's take an example of it. So an example would be a data flow network, which will be like a large network having some concurrent process where each process communicates with each other by transferring data for the data channels. Or we can take a very concrete network called electric circuit. So also this network involves the usage of input and output wires. So where we can transport the data from input to output wire using a couple of comparator multiplexers. So these actually help the data to be transferred from input wire to output wire. So this is how the butterfly sort will work by using the input and output wires and also the comparator multiplexers. Going to the next slide. Yeah, here we can see some values there on the input side and some values there on the output side, and in between we have some square boxes. So these are the actual comparator multiplexers which help the data to be transferred from input to output. And if you can see here, there are some values here. So what the comparator does is, so it will basically inspect the value which is coming to it. So based upon the value it receives, it will actually transport them to the corresponding output value. So if you can see here, like 000, so it is routed to this 000 in the output side, and also it will be routed to other 00 row where it actually where the data is actually matching to it. So we can see here the arrow is just pointing from here to here. So this is how the values are routed in the butterfly network. And coming to the next slide, here we can see a graph here. So this actually resembles a butterfly. So that's why this network is called a butterfly network, and also the sorting algorithm is named after it. And you can see here, like data is just going here and it's repeating again and again, simply resembling a butterfly. And coming to the implementation steps, there are mainly two steps in this butterfly sorting algorithm, and one is butterfly random permute, and the second one is sample partition merge sort. So let's go into the first step. Here what will happen is, here we take a unsorted input array and we just basically rearrange them, or we just call it as a permutation without actually leaking the way of the permutation. So that is the main idea behind it, right? So we shouldn't just leak about the actual information we have. So coming to the second step, we are actually sorting what are the input array we have, like after doing the permutation. That is done by using sample partition merge sort. Here we can use like any type of sorting algorithm, but in this paper, like it has been given like they have used like sample partition merge sort. So basically these are the two steps of butterfly sorting. So it will be explained much better and in lot of steps by my teammate Chetan. Chetan, you can continue.
Yes, Arvind. Can you please stop sharing the screen?
Yeah.
So coming to the implementation steps, how the butterfly sort is implemented in this research paper, we'll see that butterfly sort is based on a previous data-oblivious sort, which was sequential, and that is a bucket algorithm. And it was having a simple structure, and so does the butterfly sort. Even butterfly sort is having a very simple structure, which can be easily understood. For this, we construct a random permutation of a given input elements, which is sorted, and we do it in data oblivious way, which is one of the key step which was mentioned earlier. So in next step, we can apply any sorting algorithm that is, it need not be data oblivious. So we apply a SPMS, that is sample partition merge sort. That is one of the sorting technique which is mentioned in the paper. So let's look at the construction of random permutation. This occurs in two steps. So we create a course of random permutation, of elements by moving each element into a random bin. And in second step, we create random permutation among the elements of each bin and concatenate the bin. So here, these are the two main crucial steps. Among them, first step should be done and carried out carefully. So it will be much helpful and easier for the second step. Second step is just concatenating the bins. So coming to the first step, so what is happening in the first step is mm, process the input elements to the bin in a technique called oblivious random bin assignment. In short, it is called as ORBA. So your bin will have a size of theta log square n, and each element is given a value between 0 and beta minus 1, each of size z. So our task is to move. Each input elements into bin randomly assigned by the network. We wrote them in butterfly network obviously. That is moving each input element into the corresponding output bins. So here we see that the network structure starts from level 0 and applies to the maximum size of the bin, that is maximum of theta log square n. Again, in distributors, we see the distributors is the main component that acts in the routing network. That is, it accepts the input element to the corresponding output bins, which establish data obvious nature in them. And in return, what distributors are using the main logic inside them is AKS sorting network. They're not going much deeply into the AKS sorting network. So these are the main techniques, that is butterfly random permute and butterfly random sort, using which we get butterfly sort, that is in short form. We express it as BV sort. So this is about the overall implementation of butterfly sort algorithm. So what are the outcomes of using this butterfly sort, or in comparison with known case agnostic and data oblivious algorithms, we see that butterfly sort gives a much efficient result, which is by an exponential factor compared to previous previous work, which was taking n parallel runtime for some constant. So as a byproduct of this butterfly sort, we even see that a new oblivious sort result in standard external memory model is obtained, which is the first oblivious sort algorithm that is optimal in both work and cache complexity. Such a result was not known even in cache-aware setting, and other previous works, quoting some of them, that is Chan et al. And Goodrich works. This butterfly sort achieves even more efficiency than those prior works. That is, compared to their work, which was incurring extra log and factor in their work, this butterfly sort gives a better result in this research. And moreover, additionally, butterfly sort is a conceptually simple algorithm, and it is fairly straightforward to map it into data-oblivious algorithm, matching the current best sorting bound and other models such as the BSP, that is a bulk synchronous model, and parallel.
Now let's see a Bitonic sort in binary fork join. They use Bitonic sort instead of AKS to the smaller instances of sorting problems. AKS is typically a sorting network which has log n layers with n nodes. Their data-oblivious cache agnostic binary fork join algorithm implementation achieves higher cache complexity with maximum work and span. So in Bitonic sort, the constants in the big O notations are roughly half of the total work and the span. They convert each PRAM step into log n square time, which in turn improves the span of the algorithm. So we can say that their implementation is formally or functionally better in cache complexity and span. So they use matrix transportation to achieve high cache efficiency, and we will see it in details in the next slides. So now let's see what is Bitonic sort. As they have used PRAM Bitonic sort, it works better in parallel implementation, because in that we always compare elements in predefined sequence of comparison, and it doesn't depends on data. So Bitonic sort is a sequence of log n layers of Bitonic merges, and where each Bitonic merge is a butterfly network. So they have implemented Bitonic sort with the recursive Bitonic sort algorithm, and let's see how it works on the random array sequence. Now consider we have this array with the 8 elements. Now we will find the Bitonic sequence of 4 elements, of first 4 and second 4 elements. So we divide this whole array into 4 and the 4. So after that, after dividing it into subarray, we first sort the first 2 elements in ascending order and the second 2 elements in the descending order. Now consider this pair. We sort it in ascending order, and then these two we sort it in a descending order. So after that, next we repeat this process for the remaining pairs until we get the Bitonic sequence. So after this, we got a sequence in which the elements in the first half are arranged in ascending order, while the elements in the second half are arranged in a descending order. So next, we compare the first element with the first element of the second subarray, and second element with the second element with the second subarray. So like this, we do it like this for all the elements. So in this, we have swapped the elements if any element in the second half is small. So after that, we got the elements in the first half smaller than elements in the second half. Then again, we swap the results in 2 sequences with n by 2 each. And we recursively then repeat these steps again on every sequence until we get the single sorted sequence. Now let's elaborate the Bitonic merge. As we know, Bitonic merge is a butterfly network. But here a network is in the reverse direction. That is, the first layer of M-size Bitonic merge, each element in the input sequence is compared to element of the half away from it. in the sequence, and at last only the adjacent elements are compared. In author's algorithm, they first perform a transpose of square root of elements partition, then perform the first batch of recursive calls. Like this, they perform every batch of recursive calls. Their algorithm evaluates a single Bitonic merge in cache agnostic and binary fork join prototype. Let's elaborate this algorithm more. Consider I is the input array of m elements and m is the power of 2. So we can, in step 1, we can check if m is 1, then we return the input array I. But if m is 2, then we apply the single comparator to the pair of elements, that is m, which is 2. Then if flag is 1, we sort the returning elements in the ascent increasing order. And if flag is 0, then we sort the elements in the decreasing order. So if both are not true, then we follow the step C. In this step, we write an M array as square root of M by square root of M matrix, where each square root of M elements form a row. Then we perform a transform of this matrix, transposition of this matrix, and then let J is the matrix. So we store that matrix, we store that rows into the J. After that, we recursively call and sort it in the K square root by square root matrix, and then we perform the transpose of this matrix and stored it in L here. So like that parallelly, we recursively call the Bitonic merge and sort it in the O row and store that in the O matrix. So then in step 5, we return the final matrix. So from step 1, 2, and 3, we together evaluate the first root M layers of butterfly network, which proves that at this algorithm implements a reverse butterfly network. So in this algorithm, every element performs the same set of compare and swap with the correct elements predicted in the reverse butterfly structure. So then in step 3 does a reverse transposition and rearranges the output into the same order as they appear in the original reverse butterfly network. Applications. Now, author gives various applications of their algorithms, which are list ranking, data-oblivious primitives, tree contraction, connected components, and minimum spanning forest. Their algorithm surpasses the previous algorithm in cache-agnostic binary fork models, and other at least match the previous best known results. So first is basic data-oblivious primitives. So aggregation and propagation in a sorted arrays are primitives used by authors in simulations. Third primitive use is send receive, and it can be performed obliviously with a constant number of sorts and scans, and therefore achieves a large sort bound. Second, list ranking and applications. So in this, the author first randomly permute the input array and then apply a non-oblivious list ranking algorithm. So for Euler's tool in an unrooted tree, they use the insecure algorithm from previous work, which reduces the problem of list ranking. In this, the author use randomized algorithms because they have used randomized sorting algorithms, and therefore their algorithms are deterministic. Now, in tree contraction, the rate of decrease is fixed and it is data independent. Their ways of doing the algorithm frees up the extra space since the memory use is geometrically decreased. and a specific fraction of memory location frees up which are no longer needed. So at the end of each phase, they use oblivious sort, which removes the memory entries and reduce the work time. So next one is the connected components and minimum spanning forest. These two problems can be solved on PRAM using the n-node and n-node m-edge graph. Their theorem improves the original cited bound and increase the span by a
login factor.
So as discussed in the previous slide, we will try to derive some conclusion from this paper. So what this paper is like really doing. So this paper is presenting an efficient data-oblivious multi-thread algorithm that are cache efficient for a suite of fundamental computational tasks in CRU binary form. Joint model starting with like sorting, then paper presented how to get privacy for free for a range of the tasks in this important parallel computational model. Then the paper is also trying to like solve all the problems which was present in the prior work on data-oblivious multi-thread algorithm paper. It tried to matches or improve the insecure results. Then all the algorithm in the paper are cache agnostic. That is, the algorithm need not know the cache parameter, including the cache line size, cache size. Beside devising new algorithms, paper also makes a conceptual contribution by creating a bridge between the two lines of work from the cryptography and algorithm literatures. So yeah, it also presented a central result for asymptotic bounds in the butterfly sort, which even improves on data-oblivious algorithm in sequential cases if you want cache efficiency. Then it also tried to match the performance of SPMS, the current best CRU binary fork joint algorithm. This paper also presented the first data-oblivious algorithm that is both cache optimal and the work optimal. Then it also presented the data-oblivious sorting using beta orbo, which can be adapted to match best result in other model like BSP and the parallel external memory. Thank you. Yeah. So this is all we want to share.